Hey guys, Mr. Blue here with another sketchy at-home chemistry lesson. It's sketchy because I'm sort of running out of room here on my table a little bit, so I'm just going to try and move things around a little bit so that you guys can see things a little easier. Also trying to maximize my whiteboard space. So today let's talk about a concept called valency. Okay, so concept of valency, V-A-L-E-N-C-Y, and it's probably the most important concept to get in terms of moving forward in chemistry. So here's our periodic table, and let's start first of all by we're going to look at electrons today. That's what valency is all about. Okay, so here's our periodic table, and what we're going to do first is we're going to look at lithium. So there's our data there for lithium, and as you can see, lithium has an atomic number of 3 at the top there, and then we have our lithium there with its atomic weight of 7. So I can really just simply draw an abridged version there. We're going to have 3 protons and 4 neutrons in that nucleus because we round that 6.94 up. All right, and that's going to be, I'm going to seal my nucleus off there, and that's all we're going to talk about in terms of the nucleus. Now, your average lithium, your average lithium atom is going to have protons equals electrons. I'm not doing well today. And that basically means that because we've got 3 positive charges, I need to have 3 negative charges to even that out. Okay, so let's have a look now and see what happens with our shells. So remembering now that the capacity of that first shell, and I'm going to draw that in a nice, simple, actually, let's stick to the black. Okay, and I'm going to draw these orbital shells around here like this. Now, this is what's known as the S shell. Okay, the innermost shell is the S shell. Now, we've got 3 electrons to place, 1, 2, and 3, and we know that the capacity of that first shell, the S shell, is just 2. So we're finished there, right? Now, the next one here that I'm going to put around is, well, it means where does this electron go? It goes into the outer shell here like this. Now, the outer shell and the outermost shell with electrons in it is always what we call the valence shell. So this red one is the valence shell. Also, it's also called the S is the innermost, P is the secondmost shell. So it's the P shell. So we've got 1, 2 electrons placed, and here's our third one. Let's place it over here on the left side of my board. Okay, nice and easy there like that. So in chemistry, all we really care about is the outer shell. Okay, now what lithium is trying to do is it's trying to have a full outer shell. And it has 2 options to do that. It can either move electrons, okay, and get rid of them, send them off, or it can take electrons in and move them towards itself so it has a full outer shell. Now, basically lithium, if it were a person, has 2 decisions. It can either lose 1 and get rid of this outer shell so it's got a full S shell, or it can gain 7 so that it has a full P shell. Now, I know just based off numbers there, the easiest decision to do is to get rid of that final outer shell. Now, first of all, the next thing we need to do is do what we call a Lewis diagram. Now, what we do with the Lewis diagram is these are a simplified, instead of having to draw this stuff out all the time, we draw an abbreviation. We write the element symbol. So remember, I started with lithium, and then you'll notice that lithium's symbol is Li. Now, all we need to do is we draw a simple dot to indicate that it has 1 electron in its outer shell. Okay? Now, generally speaking, okay, lithium is very reactive because it's going to do anything to get rid of that 1 electron there like that. Okay? So that there is how we abbreviate that form. Now, let's look at something over on the other side of the periodic table. Let's wipe that away. And let's look and see what our valence shell is here for perhaps something like fluorine. Okay, so let's do fluorine quickly. So let's go, I'm just going to change my screen and let's have a look here at fluorine over on the other side there like that. Okay, so fluorine has 9 protons. It has 19 minus 9 is 10 neutrons. And again, let's draw our inner shell. Okay, And actually, there's a bit of a cheat here because as you see on my fluorine there, there's 2,7. It's already telling me the electron configuration. So that there is a simplified electron configuration there for fluorine. So we know that we have, oops, I need to do that in my nice red color. Okay, and what we have here is we have the formation. So there we go. There's my valence shell. So we're going to have 2 electrons on the inner shells, and then we're going to have 1, 2, 3, 4, 5, 6, 7. So what's going to happen, right, is very often we'll see 1, 2, 3, 4, 5, 6, 7. So it's got 7 in its outer shell. So to abbreviate that, we need to go fluorine is the symbol. 1, 2, 3, 4, 5, 6, 7. Okay, so that is how we draw the Lewis diagram for that. So it's just a much simpler way to draw it. And we only use the number of electrons in that red or valence shell, the outermost shell. Okay, so that's a really simple lesson on how to do that. Let's look finally at neon. Okay, so neon, element number 10, okay, has the electron configuration there of 2, 8. Now what this means is that neon has 10 protons, it's going to have 10 neutrons, and then here we go, that shell is going to be full, it's got 2, and its valence shell this time is also going to be full. Now what this means is that basically neon is already happy. It already has a full outer shell. Now what this does is it gives it the property of being what we call chemically inert. Okay? And inert basically means it's very unreactive because neon already has its 8 electrons and it doesn't need to gain or lose any. Now the reason why fluorine, particularly on the other hand, is so reactive is if we think back to the beginning of this mini lesson, here is our lithium. And lithium has 1 electron. This time, instead of drawing it with a dot, I'm going to draw it with a bit of an X, just to make it easier. Now, what lithium is desperate to do is it's desperate to get rid of that electron here like this. And fluorine is basically really, really keen to take that electron on. So what's going to happen is, and the reason what makes lithium and fluorine so reactive is that they can dump these really, really easily. So what would happen is lithium gives away that electron. We see it move up to here. Fluorine takes that electron on. And what happens is these two here become positively charged. This one's lost an electron, so it becomes positively charged. Okay, it's got 3 protons now, but only 2 electrons. So it's got a positive charge. Whereas fluorine has taken on an extra electron, which gives it that negative charge. Now, what happens there now between those two is that we have what we call electrostatic attraction. And we get these two bonding together to form what we call lithium fluoride. And the reason why it's called lithium fluoride is because it's changed its name. It's accepted that extra electron, and it's no longer fluorine in its atomic state. It's fluoride in its ion state. And we draw that simply like this. Now this chemical is called a salt. And the reason why it's a salt is because I took something from the left of the periodic table. I took something, lithium is a metal, and I combined it with a non-metal. Now this type of bond that forms a salt is called a ionic bond, because both of the things that are formed have become ions. And the electrostatic attraction between the positive and the negative pulls them together. I hope this helped your understanding of valency and also an introduction to ionic bonding. Thank you.